Good afternoon. We will start our 20th lecture today, and so this will be the last segment on the convolutional codes for now, before we move on to a new topic. Just to recap what we did last time, we spent most of the time in the last lecture on what I call path enumeration, and the idea here was that you wanted to look at the trellis of a convolutional code and you wanted to actually extract information about the various code words in the code, each of which corresponds to a path in the trellis. So, that is why we call it path enumeration, and for each path we associate the length of the path, which you can think of as right now as the number of message symbols for a rate 1 by n code, or it is the number of edges that is traversed by the path, and then we kept track of the input Hamming weight, that is the number of message symbols that are equal to 1, as well as the output Hamming weight, which is the Hamming weight of the code word itself. And also we derive the polynomial generator matrix for a general rate k by n convolutional code. So, perhaps I can just quickly run you through the last lecture here. So, here this part we use the modified the finite state machine and the modified trellis to actually derive the generating function, which actually gives you all the information about the various paths, and the information is in the form of power series, where the coefficients tell you how many paths have certain length, certain information weight, certain Hamming output weight. And then after that we went on to talking about a general rate k by n convolutional code, where our interest was in saying, and we did this by an example and then we took up the general case. We for this example here what we did was we took the polynomial generator matrix and then we drew the encoder. Then we said, well, what will a general rate k by n convolutional code look like, and we wrote down an equation that would describe the generation of the code symbols, and after that I went on to actually deriving the polynomial generator matrix. All right. So, that is where we left off last time. Today what we will do is we will talk about the Viterbi decoder over the additive white Gaussian noise channel. That is our principal goal, but first let me just get one other matter out of the way. If you will recall, when we were discussing rate 1 by n convolutional codes, then there was this issue of catastrophic error propagation, and there we derived a condition on to avoid catastrophic error propagation, or at least avoid having a generator matrix or a PGM that has catastrophic error propagation. So, the analogous result for the rate k by n code, I am going to actually put that down now. Okay. Theorem. And I will just put in brackets CEP, a necessary and sufficient condition on the PGM of a general rate k by n convolutional code to not have catastrophic error propagation is that the GCD of delta 1 of d comma delta n choose k of d is equal to d to the L for L greater than or equal to 0, where delta P of D, the collection as P varies from 1 to n choose k is the collection of determinants of the n choose k, k by k submatrices of G of D. Okay. So, let us zoom out a little bit. So, a necessary and sufficient condition is that if you look at all the determinants of the submatrices, then that GCD will be D to the L. I think it will become clear once we look at an example. So, supposing G of D was the same code that we discussed earlier, which is 1 plus D 1, 1 plus D, D 1 plus D 0. And now, this is a, as you can see, a 2 by 3 matrix. So, in this case k is equal to 2, n is equal to 3. So, we are interested in the determinants of all the k by k submatrices of G of D. So, that means in this case n choose k, here therefore, n choose k is equal to 3 choose 2, which is 3. So, there are 3 of these submatrices. So, delta 1 of D is just the determinant 1 plus D 1 D 1 plus D, which is turns out to be 1 plus D squared plus D. Okay. Delta 2 of D is the determinant. So, here I took the first column and the second column. Now, I will take the first column and the last column. So, that will be the determinant 1 plus D, 1 plus D, D and 0, which is D into 1 plus D, and delta 3 of D is delta 3 of D. Now, I am going to pick the second and the third columns. So, it is so that will be 1, 1 plus D, 1 plus D 0. So, this is 1 plus D the whole squared. Now, you can verify, can be verified that the GCD of 1 plus D plus D squared, D plus D squared, 1 plus D squared is actually equal to 1. And okay, so you might ask, how do I find the GCD when there are 3? We saw how to do it when there are 2. So, what you can do is you can find the GCD of 2 and then find the GCD of the third with the GCD of the first 2, okay. And how you break that up does not matter, but it is easy to see in this particular instance, because if you add the first and the second you get 1. So, anything that divides the first and the second must divide 1. So, the GCD has to be 1. So, it is fairly clear. Okay. So, that is how you would apply that. Now, the other topic on convolutional codes, and this is the title of our lecture, is how do you do Viterbi decoding over an additive white Gaussian noise channel. So, here so our channel model will be like this, and so we will work with so this is the channel model in this case. The input S belongs to plus or minus the square root of E. The noise N is distributed as 0 N 0 by 2. And the output here is y, and y is equal to S plus N. So, this will be our model, and of course, this is for a single channel use. What we will be doing is we will be using this channel over and over again, and from one use to the next, we will assume that the noise samples are independent. We will assume so E by N 0 is a measure of the SNR on the channel. And some time back when we discussed maximum likelihood decoding over the binary symmetric channel, we said the minimum probability of error decoder for the binary symmetric channel, we showed that that ended up as being minimum Hamming distance decoding. So, there is an analogous result here. Okay, so let me see if I can quickly pull that up from our earlier lectures. Okay. So, around here we were discussing the minimum probability of error decoder. This was for the binary symmetric channel, and we wrote down an expression for the probability that the code word is correctly decoded, and we set about trying to design the decoder in such a way that this probability is actually minimized, that you minimize this quantity here, and we found out that the decoder that minimizes this quantity is a maximum likelihood decoder. That is, for any given vector y, it chooses that code word such that this corresponding probability, conditional probability function is the largest. So, it is called maximum likelihood decoder. Now, in the case of the binary symmetric channel here, we went on to with the derivation, and in the derivation here we actually recognizing that the vector that is received over the binary symmetric channel belongs to a discrete ensemble, we had a summation. If y is drawn from a continuous ensemble, then the summation will be replaced by an integration sign. Apart from that, the derivation is exactly the same even over the additive white Gaussian noise channel. And again the conclusion is also the same, that if you assume that your code words are equally likely, then the minimum probability of error decoder is just one that actually chooses the code word that maximizes this. Now this was a probability mass conditional probability mass function for the binary symmetric channel. For the additive white Gaussian noise channel, this will be a probability joint probability conditional density function. Other than that, there is no difference. So let us go back here. So as in the case of the binary symmetric channel, it can be shown that when all code words are equally likely, then the decoder that minimizes the probability of code word error is the maximum likelihood decoder, where you actually say use the algorithm that choose that code word that maximizes probability of y given the code word. Now just one comment over here. When I wrote down the channel model here, I put down as input S, which is plus or minus, but our code has always been 0 or 1. So how do we make the connection? So the connection is easy enough, where S I is equal to -1 to the C I times root E. So this is a mapping. So this thing here is the code symbol, whereas this here is the symbol transmitted. Okay. All right. So now that we've cleared that up, let's see if we can get more information about the decoder. Now, in the case of a convolutional code, your C, your code word, your C is really the collection of vectors So, this is what your code word will look like. It will be the collection of all n tuple outputs. So, then in this case P of y given C breaks down to the product t is equal to 0 to n minus 1, the product j is equal to 1 to n, P of y t j given v t j, and where P of y t j given v t j is 1 upon root 2 pi n 0 by 2 exponential minus 1 upon 2 n 0 by 2 y t j minus s t j the whole square, and s t j is minus 1 to the v I will just give myself some more space to write that. So, s t j is root e minus 1 to the v sub j of t. All right. So, let me just zoom in so that you get a better perspective. So, maximum likelihood code word decoding asks you to actually select that code word which maximizes this quantity P of y given C. But P of y given C is really the product of several terms, and each of which actually looks like this. Now, it is clear that if you wanted to maximize this quantity, what you really need to do is minimize this exponent. Because of the negative sign, you want to minimize this. These are constants which do not affect the maximization. So, you want to actually minimize this distance. So, it is clear therefore that maximum likelihood decoding calls for minimizing the quantity, the sum t is equal to 0 to n minus 1, j is equal to 1 to n, y t of j minus s t of j the whole squared. Now, this in turn can be expanded into y t j squared minus twice y t j s t j plus STJ squared. So, you want to minimize this, you are interested in minimizing this quantity, but this thing is a constant, it does not depend upon the code word, because this maximization that you are trying to do is aimed at trying to differentiate between two code words. But now if you have a term which is independent of the code words, you are free to ignore it. So, we can drop this term. Now, on the other hand, or rather in similar on a similar note, this thing really, if you look at the expression for ST, if you square ST you will always get E, okay, just from this expression here. If you square this quantity, the dependence on the code symbol disappears and you will just get E. So, again you get a quantity that is independent of the code word and therefore can be dropped. Okay. So, this is just E. So, this can be dropped. So, it is clear that from this and thus maximum likelihood decoding is aimed at maximizing again the inner product which is square root of E, the term t is equal to 0 to n minus 1, j is equal to 1 to n y t j minus 1 to the v minus 1 to the v t j. Again here once again this constant root is of no consequence. So, then this is what we choose to minimize, choose to maximize. Okay. So, what we want to do now, you can recognize that this is really an inner product between two vectors. One is the stream of symbols y sub t j and the other is the corresponding code symbols in plus minus 1 format. You want to take their inner product and actually choose that code word which actually maximizes this inner product. So, now let us see if we can actually look at this computation on the trellis, and I am going to try something new here. I am going to try to do this on a PowerPoint slide. Okay. So, here this now is the same trellis that we had earlier when we were dealing with the binary symmetric channel, and we actually carried out decoding over the binary symmetric channel. We had drawn a trellis and we actually looked at decoding. So, this is the same trellis, it is the same code. The only difference here is that now what we have, what I have put down at the top are the two received symbols corresponding to each branch of the trellis. Okay. So, these are the received symbols YT1, YT2, okay. For t equal to 0, this is YT1, YT2 for t equal to 1 and so on. Okay. And in this case we have 1, 2, 3, 4, 5, 6, 7, 8. So, in fact n is equal to 8. Okay. So, we are looking at decoding code words whose branch length on the trellis is 8. Okay. That corresponds to 8 message symbols and 16 output symbols. However, you must keep in mind that this is a terminated trellis, because here we start the trellis in the all 0 state, but then we bring it back to the all 0 state. So, the last two message symbols are 0 and thus do not contain information. So, there are 6 message symbols, but all that I want to show you here is simply the functioning of the decoder for this case. Now keep in mind that all that you had to do was take the inner product between the plus minus 1 version of the code symbols and the received vector. Now the plus minus 1, now I have written in very small print here 0 0 just to allow me to keep track of the calculations. So you may not be able to see it on your screen, but it is the same trellis as before. So the 0 0 here translates in the plus minus 1 version to 1 1. So when you take the inner product of 1 1 and 3 4, this is 7. So what I am going to do here is I am going to write down the corresponding inner products corresponding to every one of these branches. What we are aiming for is the inner product between the plus minus 1 version of the code word and the entire received vector, but we will actually do it at a branch at a time, and it is clear from the nature of the inner product that you can actually compute inner products per branch and then add them up along all the branches making up a path, and that way you get the inner product for the entire path, right. So that is clear. So that is what we are going to do. So I am just going to simply write down these inner products. So let me see if I can pick an ink color. I guess I should pick red, and I am going to pick a ballpoint pen. So let us see if I can put down now. Here the 0 0 here corresponds to 1 1, so that is 3 plus 4, that is 7. Okay, so I guess the color did not work. So let us try that again. So that is 7. Okay. And for the next symbol, similarly it is minus 2 plus 0, that is minus 2. Okay, I see that on your screen it is not really showing up very well. So perhaps that was not such a good idea after all. Let me get back to black. Okay, so let me erase these and get back to black. We will stick with black and the ballpoint pen and put down the numbers, and hopefully that will come out okay. So this is then 7, this is minus 2, 2, 1, 7, minus 2, 2, minus 9. And now I want to write down the corresponding numbers for all the branches in the trellis. Next let us look at the 1 1 branches. So the 1 1 branches are corresponds to minus 1 in the plus minus 1 format. So it is minus 3 minus 4. So I have to write down exactly the same number as I did earlier, except that I have to flip the sign. So if this was 7, then this will be minus 7, and looking at this figure it looks like a good place to put that down would be here. So that is minus 7, that is 2, that is minus 2, minus 1, minus 7, 2. Okay. Now I want to put down the corresponding numbers corresponding to this 1 0 segment. 1 0 means minus and a plus. Okay. So that means that I take the second symbol as it is, but the first symbol I change the sign and then I add. So that's this will become 2, this will become minus 6, minus 7, 1, minus 8 and minus 10. Okay. So there are 8 branches, so I have 5 more to go. Now let us look at this branch, the 0 1 branch, which says take the first one with the plus and the second with the minus. So here this would be a 3 minus 4. So I would put down a minus 1, a minus 2, excuse me. Okay, let me try that again. So here I had the wrong branch. So here I need to take the first, this is a 0 1 branch. So I need to take the first symbol with a plus and the second with a minus. So this is minus 2, and this one is 6, this one is 7, this is that one is minus 1. Minus 1, this one is 8. Okay. And all right, so I have done. Now let us look at the branches along the bottom of the trellis. That is a 1 0. So that tells you that you take the first with a negative sign. So that is minus 6, minus 7, 1, minus 8, and then we have these 1, 2, 3, 4, 5, 6 segments over here, which correspond to a 1 1. So these would be, you negate both signs, so that this would be minus 4 plus 2, which is minus 2, minus 4 plus 3, which is minus 1, minus 3 minus 4 is minus 7, minus 3 plus 5 is 2, minus 6 plus 4 is minus 2. Okay. So we have now drawn for, I think, most of the outputs. There is there are two paths which are 0 1 here. So this 7 and this 6. Okay. So let me just write down some numbers here quickly. So this is also a 6, also a 7, minus 1, 8. And over here this is a 0 1, so that would be 6 plus 4, this would be a 10, and this one would be a 9. I think the only one that I have not included is the 0 0 segment, but I can fill that in easier. So that is 2 1 7 minus 2. Okay, so it looks like a little complicated, but all that I want to say is that if you look at actually this trellis, then all the inner product of associated with every code word is can be computed from the numbers that are actually shown here. But what you can actually do is you can proceed as in the case of the Viterbi decoder. You can proceed as in the case of the Viterbi decoder. Let us see if I can get the arrow back. You can proceed as in the case of the Viterbi decoder for the binary symmetric channel. So what you do is you go from left to right and you are trying to look at the code word that maximizes the this inner product. So you start over here, this is 0, and now you have a 7 and a minus 7. So these metrics are also transferred to these nodes. Then thereafter you accumulate the metric. So this is 7 and minus 2, that is 5. So here the metric here is 7 plus minus 2 5, this is 7 plus 2 9, minus 7 plus 2 minus 5, minus 7 plus minus 2 minus 9. Okay. So what you can actually do is you can keep track of metrics. So this is called the metric. So this inner product, partial inner product, is called the branch metric, and the total inner product is the code word metric. You can compute, or a path metric. You can compute the path metric by adding the branch metrics, and just like in the case of the binary symmetric channel, the real progress is made in decoding when you arrive at a node where there are two contending paths and you can choose between one of them. For example, here the total metric is 7 minus 2 plus 2, which is 7, or the other choice is minus 7 plus 2 minus 2, which is minus 7. So, you have choice between 7 or minus 7, and of course, you will pick the 7. Okay. So, that means at this point you have a loser, in the sense that there is no way that a code word which begins in the trellis like this can ever go on to become the code word that maximizes the metric. So, you can actually discard that. So, now you see that once you have written down these numbers and you so earlier the numbers were all integers, they were all positive, and you are looking to minimize the metric, path metric. Here the numbers are real numbers, and they could be plus and minus, and you are looking to maximize the metric. But other than that, the decoding proceeds exactly the same as before, and you can actually go ahead and choose the winning path just by going section by section. Okay. And at every node, what you do is you discard at every node level, you discard one path at each node. Okay, and that is where the complexity saving comes in. But I think that given that the display is still not very clear legible on this, I will not pursue this any further. Hopefully the meaning is clear, and so I will end the discussion on the decoding on this. It is very similar to what we did for the binary symmetric channel. So, I will just write a few comments to accompany what I just told you. Each code word is associated to a path. The associated inner product is called the path metric. Each path metric is the sum of branch metrics and decoding proceeds exactly as in the case of the binary symmetric channel, except for the fact that our branch metrics are now real numbers either positive or negative, as opposed to being integers, as opposed to positive integers in the case of the binary symmetric channel. And finally, we are looking to maximize path matrix and not seeking the path with minimum metric as in the case of the binary symmetric channel. Okay. So, decoding proceeds exactly as in the case of the binary symmetric channel, except for the fact that our branch metrics are now real numbers, either positive or negative, as opposed to positive integers in the case of the binary symmetric channel. Also, we are looking to maximize the path metric and not seeking the path with minimum metric as in the case of the binary symmetric channel. So, we will leave it at that. And finally, I just want to put down a couple of formulae without proof. So, it turns out so the title is upper bound on the bit error probability. It turns out that the generating function A and L I D derived earlier can be used to provide an upper bound on the probability of bit error incurred while employing the Viterbi decoder. Now, just a note here, the Viterbi decoder is actually designed to select that code word whose which minimizes the probability of code word error. So, it's somewhat strange to actually say that is the basis of our decoding algorithm, and yet when we talk about performance analysis in terms of probability of error, we are talking about the bit error probability, but that is just the way it is. It turns out that it is convenient so the bit error, an upper bound on the bit error probability is conveniently derived and is of the greater relevance, because the bit error probability is a better reflection of performance of a code. Okay. So, it is better and it is feasible. So, that is the reason we do it. So, again unfortunately, we do not have the time to go through the derivation, it will take us a little too much out of the way. So, I will just put down the formula and leave it like this. There are two different formulas depending upon whether you are looking at the binary symmetric channel or the AWGN channel. So, case 1, in the case of the binary symmetric channel, we have that the probability of bit error is less than or equal to 1 upon k times del by del I of A and L I D, where you set, after differentiating, you set L equal to 1, I is equal to 1, and you set D is equal to twice root epsilon into 1 minus epsilon. Okay. And there is an analogous formula. So, here of course, epsilon is the crossover probability of the binary symmetric channel, right. So, here we are talking about okay. So, this is the setting for this, and of course, here what we mean by this is a reference to the bit error probability. Okay, bit means message bit error probability. So, you take the derivative of L of I d with respect to I, and then you set L equal to 1, I equal to 1, and D is equal to 2 times square root of epsilon 1 minus epsilon. Of course, since you are going to, since L is not involved in the derivation, you can actually set L equal to 1 to begin with, but that's okay. All right. Then case 2, in the case of the AWGN channel, the probability of error expression is a little more complicated in terms of writing it down. So, this is, it is in terms of the Q function, okay. So, the expression is a little more complicated, but just perhaps by way of partial explanation, the heart of the formula really lies in this, and you could actually use this, except that somebody realized that you could actually make it a little bit tighter if you actually wrote it in this form. Okay. Now, only before I close, I should just mention, perhaps let me just summarize what we have done today. Let me zoom out so that you can take a look at our slides here. So, today I first of all wrote down, so today was kind of like a cataloging class when we actually write down or list down all the topics in an effort to try to provide a somewhat complete discussion on convolutional codes. As I mentioned earlier, since coding theory has branched out and developed so many methods, we do not have the time to pursue this in the depth that we would have earlier. So, for this reason, this is a little bit rushed. So, what we did was we actually wrote down the condition to avoid coming up with a polynomial generator matrix that has catastrophic error propagation, and the condition was in terms of the determinants of the submatrices and their GCD. And then after that, we actually talked about Viterbi decoding over the additive white Gaussian noise channel and we went through an example, perhaps not completely, but at least hopefully sufficiently to give you an idea what it is like, and then I wrote down expressions for the bit error probability of the convolutional code under Viterbi decoding. The only thing that perhaps remains to be done is to explain what D free is. I think that so I will say it quickly in words and maybe come down to back to this next time. So, when we in the last class, when we wrote down this generating function here, so let me zoom in into this one here. When we wrote down the generating function here, then when you expand this in a power series, the smallest exponent of D is called D free, but perhaps I will say a few words about that next time and then begin our next topic. All right. So, with that we will end. Thank you.